All right, again, good morning. Welcome back to MAC1140. Today we're going to continue our discussion of logarithms, but before we do that, I want to talk just a little bit about the exam. So your exams have been graded, the scores are all in, that's all updated. I think whether you took the makeup test or took the original test, and whether you took it at the testing center or took it online, all 4 of those sets have been graded. If yours is missing, I do think there's one individual for whom I haven't received the written work yet, and I've reached out to her. It doesn't look like she's here right now anyway. So yeah, pretty sure everybody who's here should be all squared away, which is good news. There is some not so good news. So we're going to take a minute here at the start of class to talk about something that I talked about at the start of the semester. But first, let's get in here and do the thing, get the title card up, and that way the videos will be cohesive. So here we go. Focus. All right, let's start. This is MAC1140 section OR1, which is pre-calc. And today is the what, the 7th, right? 8th. Oh, it's the 8th. Focus. Focus. 11, 8, 21. All right. So as promised today, more with logarithms. Yeah, so the test. The scores weren't bad, right? That's you know, I'm not here to like berate you for not doing well on the test. You guys know I have access to the same cheating tools you have, right? Like I have Photomath and Mathway on my phone too. Any math professor who, especially teaching online, doesn't run their own shit through Photomath, Mathway, Wolfram, Symbolab, all of those, is a fool. I'm not such a person. So I do run my own shit through Photomath, Mathway, Symbolab, Wolfram, whatever else I can find. So when you verbatim copy shit down from Mathway and from Photomath, and you put that on my test, I know it. There's no nice way to say this. A lot of you cheated on the test. Some of you cheated so blatantly that I outright wrote, do not cheat on my tests on your written work. If you haven't reviewed the written work, please review the written work. I don't, you know, I'm kind of at a loss. So at the start of the semester, I told you guys, if you need more time for a test, I'm happy to give you time to prepare. You know, if you're feeling stressed out, I can give you a few extra days. That's why we have the makeup thing. And this is why I grade 4 versions of every test, which is a pain in my ass, but I don't mind doing it, right? Because I'm sympathetic with the situation. I've been there myself where you're feeling stressed out. And I know that in this setting, right, especially online, when you're feeling that kind of stress, that temptation to cheat is much greater. It's not an ego thing, right? It's not like I don't want you to cheat on my test because somehow I am special over all the other people teaching these classes, and because everybody else's tests get cheated on, like I think I should somehow get some sort of special respect by you guys not cheating. It's because I want you to understand the material. And more importantly, I need your grade to be a reflection of your skills, because that's the only way, it's the only way that higher education maintains its value in this country. If your grades are not a reflection of your skills, the world will discover that. And by the world, I don't just mean like people who hire you for jobs down the road. I know most of you are probably not going to need to calculate an average rate of change by hand at your job of choice. Now, some of you may. And certainly understanding the concept there of a rate of change, how inputs and outputs move together, and how the relative size of the output compared to the input is an important thing, as are all the other things that we've talked about, like factoring polynomials and you know, all the content from this class. Every single piece has some deep conceptual link to a thought pattern that will be relevant down the road in your life. certainly I don't take out a piece of paper and scribble down any calculus when I go on road trips, but I absolutely do calculus estimations in my head to tell me when to stop for gas or when to hit the brakes, or all of these different things. Everywhere in your world, you've got kinematics, you've got things in motion, things changing. And all of that, if you want to understand that, all of that is calculus. And the stuff we teach in this class are the fundamentals necessary to learn calculus. So by not accurately representing your skills on the test, you are screwing yourself. And it's very easy. Let me tell you how many times I've seen it, and not just in students, but in people I know in my personal life, where you float through one class by doing things that maybe you shouldn't do, and then the next class or two classes down, it catches you out, and now you're in this, you think it's a rough situation here. It's incredibly rough when you're two classes deep into a calculus sequence and you don't have the background skills that you need. You have to work so much harder to even have a chance. I'm trying to decide what to do. So I think I mentioned to you guys at the beginning of the semester, when we did the syllabus review at the very, very start of the term, that the largest number of people I've ever caught cheating on a single test was like 8 or 9. And that was a Calc 2 class last fall, and it was on the final. The way that happened is that I had caught most of those kids cheating earlier in the semester, and I gave them stern warnings, right? Things like writing, don't cheat on my test on their written work, and sometimes talking to them like this. And that didn't work. Right. And so when the final came around and I still saw those same people cheating, I really didn't have a choice but to go ahead and start a conduct trial for each of them. And that was rough on them, and it was rough on me, and it was unpleasant for everybody involved. I have a choice here, right? So I can start a conduct trial for everybody who cheated on this last test. And that's what I should do, right? Let's just be clear. That is what the college expects me to do. And it's what I'm mostly inclined to do. Or I can try to handle this the way I handled that Calc 2 class last year, and imagine that if I'm somehow stern enough with you in this conversation, that I will scare you into not cheating on future tests. Here's what I'm thinking. I'll be honest, and I would like to say that I have a solution planned out, but I really don't, right? I'm thinking on my feet here. I know we make mistakes, right? People make mistakes. That's normal. Even mistakes that they wouldn't normally make under high stress situations. And I don't want to trash anybody's academic career over a single bad judgment call. I'm not gonna come to a conclusion right now. I think trying to decide exactly what to do at this moment isn't wise. But I'll just say this, right? Regardless of how we end up handling this particular instance, right? Whether those of you who cheated on this test get a conduct trial or not, if I see anything, fucking anything on exam 3 or on the final, anything at all, I promise you, I absolutely promise you, you'll be getting a letter to Rodkin's office. You'll be getting called in, and you'll have to sit down at a table with like 15, 20 people, half of them faculty, third of them administrators, third of them fellow students. And you'll have to explain why you cheated on the test, and you'll have to sit there and listen to me recount exactly what you did. And then you'll have to wait while Rodkin and the group of folks on the conduct board decide what to do. Just so you know, right, the standard sanctions for cheating on a test are the gentlest one is a 0 on the test and a note in your file. The next step up is an F in the class and a note on your file. Step up after that is a ZF on your transcript. So rather than just a regular F in the class, there's a special grade called a ZF, which is a failure for academic misconduct. So that, well, the notes that go into your file are only here at Santa Fe. Those don't follow you to your next institution. A ZF on your transcript will follow you to the next institution. And for a first offense, it's not uncommon to see any one of those 3 sanctions, right? If it's a you have a chance in those situations to explain yourself, and if the conduct board feels that that this is something that, you know, one-time mistake, you know, never going to do it again, high stress situation, just couldn't handle it, whatever. Maybe a 0 on the test and nothing else besides the letter in your record here at Santa Fe is what happens. But I've also seen plenty of first-time cheaters get ZFs, right? You fail the class and you get the failure for academic misconduct on your transcript. That is a stinger right there. That will fuck up your transfer. If you're, I assume many of you are hoping to transfer. It also looks bad anywhere, jobs that, you know, want to see your transcripts. It can go beyond that. If you've been caught cheating before, even if there were not any sanctions, right? If you've ever had a letter sent to the academic conduct people in the past, you can be expelled for this, right? You can have your enrollment at Santa Fe terminated. So I'm gonna think long and hard about this. I really am. Like I said, it's not my desire to fuck up anybody's academic career because they made a mistake or a bad judgment call under a high stress situation. At the same time, I've provided every relief valve I can, right? There's really not much more I can do to try to dissuade you from cheating and give you opportunities to do other stuff. So we got to do something. We got to do something. Haven't decided exactly what to do with this instance, but I absolutely promise you, if I see anything, right? And just because you didn't get a little note on your test doesn't mean I don't know you're fucking cheated, right? There are plenty of cases there where I was like, oh, this looks like what came from Mathway. It just, you know, doesn't have a few of the in-between steps that Mathway showed. Or this looks a lot like the answer from Symbolab, but it's, you know, letters have been changed or something, right? I recognize this stuff. And I'm not saying I'm perfect. There probably were people who cheated that I didn't notice, but there are also a lot of people who I noticed cheating that I didn't make comments on the test because I didn't feel like the cheating was obvious enough for me to like get into an argument about. But if I see anything like that on exam 3 or on the final, I don't care about getting into the argument. I'll just send the letter to Rodkin and let you guys sort it out with the conduct board. So that's that, right? That's that. Please, for the love of fucking God, do not cheat on my tests. You will trash your own education, and long-term, you will trash higher education in the United States for everybody. Because if the value of these degrees are not maintained, you guys all, I'm sure, know some folks who are politically conservative and anti-higher education. Not to say everybody who's conservative is anti-higher education, but people who are anti-higher education because they believe there's no value in it. This is why, right? This is why, because it's possible to get through some classes without learning the material. And then when you're out there in the world interacting with other folks, they realize that you haven't actually learned the stuff. And they say, well, why did you spend so many thousands of dollars and years going to college? If you want your degree to be worth something down the road, stop cheating. All right, that's enough. Let's get back to logarithms. Okay. By the way, if you didn't cheat, thank you. And I'm so sorry. I'm so sorry. I know this is not a pleasant conversation. And if you did accurately represent your skills on the test, thank you so much. I know that the majority of you did do that, right? And I definitely appreciate that. I saw lots and lots of really good efforts. I saw plenty of people making little mistakes, but doing the majority of things correctly. And that's what I want to see. It's okay if you make a mistake. I want that to be very clear. It's okay to not get 100%. It's okay to not have every step of every problem perfect. That's normal. That's how it should be. It's okay. And thank you for those of you who are brave enough to do that. That really means a lot. And again, I'm sorry to those of you who didn't do any of that stuff for the last, whatever, 5 minutes. Okay, logarithms. So 0 things 0. I'm opening up a second homework set for you on logs. It's homework 19. Take a quick peek at it here. This is the stuff we're going to talk about today. We've talked a little bit about logs in the past. I have shown you what they are, more or less. And you've learned how to evaluate them, but we haven't talked very much about graphing them. So I do want today to talk a little bit about graphing logarithms, graphing both kind of by plotting points, by thinking about them as inverses to other functions, and then transformations of those, and then things like domains, right? So this is the new homework set. And this homework set is going to be due on Wednesday. It's a relatively short homework set. It is the part 2 to section 4.3. It's open this morning, and it is going to be due on Wednesday of this week so that we can move forwards. I'm going to remind you sort of the basics of logarithms, definitions, and stuff here, and then we'll look at some graphs. Okay, so Let's say definition. So the base A logarithm is the inverse function, right, f inverse of x for the base A exponential, which is f of x equals A to the x. And it's denoted here, f inverse of x equals log sub A of x. All right, so this is the definition of the logarithm, right? It's the inverse of the exponential. The number A here, that base, remember, is always a positive number because it is the base of an exponential function. Those always have to be positive. And there are a few immediate consequences of this definition. The first, remember, if you plug into this original function the inverse function, or plug into this inverse function the original function, they should annihilate one another and just leave you with x. So this first one is that if you take the base A logarithm of A to the x, that's always just going to be x. And if you raise A to the power of the base A logarithm of x, that's also always going to be x. And I think when we mentioned this last time, oh, my blue is gone. Damn. I mentioned this last time. I put it in a blue box, called it a blue box statement. I put it in a purple box today because I don't have blue. All right. These two properties are most useful for solving equations, right? Like that 2 to the x equals 3 equation. We talked about that a little bit in our very first lecture where we mentioned logarithms. It's really this statement that's going to allow us to solve that equation and give the exact answer. And we'll take a look at that in a little bit. Other immediate consequences of this, let me just, let's see, I guess there's no sense in really running right back through all of that. Yeah, we've got plenty of practice just evaluating the things. I'll write them down. So the other way we characterize this, we said can also be said as the log base A of x is equal to y if and only if, or means A to the y equals x. This also deserves to go in the box. So these are kind of our ways of thinking about what logarithms are. And then we had some special notation. The base 10 logarithm of some number is often just written as log without any base. And the base E logarithm is often just written as the ln of x, ln standing for natural logarithm, or logarithm natural. So formally, these are what logarithms are, right? They are the inverses to exponentials. And the definition of an inverse function means this, means when you plug f inverse into f or f into f inverse, you always simplify to x. Another way of saying that is that if x is the input for the logarithm and y is the output, then if you take the associated exponential, y is the input and x is the output, right? And this is the same thing as what we say when we graph these things about reflecting over the line y equals x. Special notation here, these are the two buttons on your calculator that you have for logarithms. Oh, right. Awesome. Okay. Let me just 1 second to triple check something, because I don't want to be super redundant here. I want to see exactly where we left off last time. Yeah, so you guys, we haven't met since the 3rd. And did we get through to graphing with transformations? No, we did all the evaluation. Oh, we did graph a few transformations. Yeah, okay, just 1 or 2. This is you guys, right? 401 from the 3rd. Yeah, okay. So we're going to go straight back to graphing some transformations. I'm going to sketch the natural log for you. Here we go. All right. So we're going to sketch the graph of the natural logarithm by taking the natural exponential and reflecting all the points over the line y equals x, right? Because this is the inverse to this. E to the x, you'll recall, he looks like any other growing exponential. We of course have the point here 0, 1. And the point here 1, e. And the point here 2, e squared. Over here we have the point -1, e to the -1, or -1, 1 over e. All right, so I'll use these points as my sort of fundamental points, or the points that I can start with. And we have this horizontal asymptote, which is the line y equals 0. So that's e to the x. And what I want to do is reflect all of the points on this graph, not just the ones that I've labeled, but all of the points along this curve over the line y equals x to get the graph of the inverse function, which is the natural log function. Sorry, my cat's being so he's begging at the door. My wife opens the door and then he runs away. What that means is we're going to swap all of these ordered pairs, like 2, e squared is going to become e squared, 2. 1, e is going to become e, 1. 0, 1 is going to become 1, 0. And -1, 1 over e is going to become 1 over e, -1. So the graph of the logarithm then, the solution, we'll do it in purple. So I'll say this points on e to the x, just to make sure we're clear, points on ln x. So we have -1, 1 over e on e to the x, which means 1 over e, -1 will be on the natural log. We have 0, 1 on e to the x, which means 1, 0 will be on the natural log. We have 1, e on e to the x, which means e, 1 will be on the natural log, and 2, e squared on e to the x means e squared, 2 will be on the natural log. So again, the sort of basic idea is that these logarithms, there is no nice algebra formula for them in terms of like powers of x or square roots or anything like that. There's no mismatch of those things that will give you the inverse to an exponential function. So we define the logarithm to be the inverse of the exponential function, and then all of the properties for the logarithm, they have to be cooked up just using facts about inverses. Remember, to reflect over the line y equals x means to swap x and y. Right, so if -1, 1 over e is on the original, then 1 over e, -1 is on the inverse. That's all stuff we tested on exam 1. So let's come down here. Sorry. Let's come down here and sketch our graph of the natural log using these points. And then we're going to reiterate some of the statements about domain and range that we made last Wednesday. This is the graph of the natural log function. Let me mark this as 1, 2, 3, way out here, 4, 5, 6, something like this, right? Mark this as -1. So we've got 1, 0. 1 over e, well, e is, remember, about 2.7, kind of close to 3. So 1 over e is kind of close to 1/3. So that would be like right here. So right here is the point 1 over e, -1. That's why I've chosen the x scale to be kind of large, so you can see that. Here's the point 1, 0. The next guy would be e, 1. So e itself is like right here, 2.7-ish. So e, 1. Like right here. On my next point, e squared, 2, I'm gonna have to mess with this a little bit. I'm gonna say e squared is right here. E squared should be pretty close to 9. And I just don't have room to keep the scale completely accurate. So I'm gonna say this is that point, e squared, 2. And here's that point, e, 1. Some mistakes people make when they graph logarithm functions is to assume that the graph begins at this x-intercept, but it doesn't. You know, there are other points down here also. Like, is there a point whose y value is -2? Yes, it would be 1 over e squared, or e to the -2, -2. And in fact, we go all the way down here. There's a vertical asymptote. This horizontal asymptote, when you reflect everything over the line y equals x, becomes this vertical asymptote. And then here's the rest of that graph. And just like exponentials grow very quickly, logarithms, as their inverses, they grow incredibly slowly. So this guy, he does continue to grow as you go out that way, and he will eventually make it all the way up, however high you want. But he grows very, very slowly. I know we graphed other logarithms last time, and we said all the log graphs look the same, but I want to emphasize this one in some detail, because the natural log function is the logarithm that we always use, in the same way that e to the x is everybody's favorite exponential, ln of x is everybody's favorite logarithm. And when you get into your calculus classes, it will 100% be assumed that you know this graph. So please take the time to get this in your notes, make sure everything is clear. You know some of these points, right? At least the ones from the table here. And you know the shape, you know the asymptote. The domain of this function is the range of e to the x. which is 0 to infinity, because all the x values on e to the x become y values here, and all the y values on e to the x become x values here. So the range of the original is the domain of the inverse, and the range of the inverse is the domain of the original, and the domain of e to the x was negative infinity to infinity. So these are the facts about the graph of the natural logarithm that you need to know in order to start graphing transformations of it. And you will have to graph transformations of this function. You'll have to shift it left, right, up, down, flip it over, all that stuff. That reminds me. There is one more, I'll talk about it at the end of class. Remind me I need to talk about jellos at the end of the class. There's a special assignment that I'm going to give you to earn some points back on the last midterm. So the fact that the domain of this logarithm and all logarithms is 0 to infinity means we have a new domain red flag. Remember our list of domain red flags from the start of the semester? So when you're trying to find domains of functions algebraically, if you don't happen to have the graph of that exact function, then we had to look out for certain sort of algebra signals that told us there could be a domain restriction coming from that particular algebra feature. The ones we had before were variables downstairs in a fraction, and for these, you had to make sure the bottom was not 0. Right, so if you had some variable quantity in the denominator of a fraction anywhere in your expression, and you're looking for the domain of that function, you had to figure out what values of that variable would make the bottom 0, and then kick those out. We also had the red flag, which was variables under even roots. And here we had to make sure that the inside was greater than or equal to 0, right? Because you don't want to take the square root or fourth root or sixth root of a negative number. The new domain red flag, right? Since the domain of this logarithm and any logarithm is 0 to infinity, right? You notice there's no graph over here where the x values are negative. That means you cannot plug a negative number into a logarithm. So if you have a variable inside the logarithm, this comes with its own new restriction, and that is that the inside is strictly greater than 0. Right? We cannot take the log any base of 0. The natural log or base 2 log of 0 is undefined. That's this vertical asymptote here. And definitely cannot take the log of a negative number. So if you're trying to find the domain of a function that involves some logarithm stuff, you need to make sure that the inside of that logarithm is strictly greater than 0. And I know this isn't what you want to hear, but this means there's going to be more inequality solving, right? Just like the last problem on exam 2, that rational inequality, problems like that can now show up as domain finding problems for logarithms. And I'd like to look at a couple examples of that, and then we'll do some more transformation graphing. Maybe we'll start with a combination of both, actually. Let's say here, find the domain for f of x equals the natural log of x plus 2. And so let me do negative natural log of x plus 2 and sketch the graph. All right, I don't want to beat the transformation stuff up too much here because you You've already seen some of it, and you will have some more of it to practice on a worksheet I'm going to send out. But let's start with this. So, given what we just said, even without the graph, how would you find the domain of this function? What domain red flags are present here? I promise it's not a trick question.
-2?
Yeah, definitely the variables inside the logarithm are the red flag, and something to do with -2 is important, right? That's correct. But I want to be a little bit more detailed. So the domain red flag is variables inside logarithms. So we need to make sure that the inside is strictly greater than 0. In other words, I need to make sure that x plus 2 is strictly greater than 0. And that's the same as saying x is greater than -2. So this is our domain, i.e. the domain is the interval, all the x's that are strictly bigger than -2, that's -2 to infinity. And we'll look at more complicated versions of the domain finding problem in a separate example. Next, what we want to do is sketch the graph. So my parent function is y equals the ln of x. We'll start with the graph of the natural logarithm. So I'll resketch here, just so. This is the point 1, 0. Here's the point, I'm sorry. Yeah, we'll say it's okay. Yeah, here's the point e, 1. And over here is the point e squared, 2. And if you like, down here, we could say this is 1 over e, -1. And we have this vertical asymptote, x equals 0. What transformations do I need to apply? To get the graph of the negative ln of x plus 2 from this graph. There's two transformations. What are they? One of the transformations comes from the +2 inside here, and it's hinted at strongly by this domain. The other transformation comes from this negative on the outside. So what transformation comes from the x plus 2? If I add 2 on the inside of a function, what does that do to the graph?
Make it go left and right?
Yeah. In particular here, since I'm adding 2, you're correct that adding on the inside shifts us left and right. And the specific transformation here, swapping x for x plus 2, is going to drag us to the left 2 units. And we always do horizontal stuff before vertical stuff. So this would be my first transformation. All right, what about the negative on the outside? What does that do?
I know it reflects it across one of the axes.
Yeah, that's correct. So outside stuff is vertical stuff, right? So this is going to be a vertical reflection. In other words, it's a reflection over the x-axis. All right, so those are the transformations we need to apply. I'm going to shift left 2 units. Maybe I'll do the shift left first. Let's draw what that gives us. That means my vertical asymptote is going to move from x equals 0 to x equals -2. And the shape of the graph will stay the same. I'm just doing that one thing right now. You can follow a few points. 1, 0 comes left 1 to 0, 0, and left one more to -1, 0. We can kind of use that as our like base here to see what the graph is going to look like. That's the picture we get. And the rest of the points are a little bit tricky to describe because these x values are not integers. So like subtracting 2 from these is just going to give you, I'll put it, let's see, here. So this would be e minus 2, 1. And the point from e squared, 2 would go to e squared minus 2, 2. And down here, this guy, let's see, I don't really have space to draw him in there. Let's say this guy is 1 over e minus 2, -1. All right, so that's the left shift done. That's my x-axis. This is my y-axis. And then the vertical reflection, I'm going to take this graph and kind of spin it around like it's on a barbecue spit. I'm going to flip it over the x-axis. So my final graph, this one nice and big. That vertical flip isn't going to alter my asymptote at all. But this whole piece down here is going to get flipped up to here. So I'll now be approaching that asymptote like this. The point -1, 0 is going to stay -1, 0. And the rest of the picture is going to look as you expect when you flip this thing over. Something like that. E minus 2, 1, when I flip him over, he's going to come down here to e minus 2, -1. E squared minus 2, +2 is going to come down here to e squared minus 2, -2. And this point, 1 over e minus 2, -1 is going to become 1 over e minus 2, +1. And this is it. This is the graph y equals -ln of x plus 2. So the homework set that I opened up for you guys this morning has stuff like this, right? Just transformations of logarithms, stating domains and ranges, that sort of thing. For fun here, we've already said what the domain is, right? The domain, we were able to find algebraically is -2 to infinity. And if all I wanted was the domain, I wouldn't want to have to go through this whole graphing process, right? It would be nice to just get this the way we did at the start. The range is a little trickier. Ranges in general do require that you have the graph. And the range here, we can see we're going to go all the way up to positive infinity here. And eventually down this way, we will get to negative infinity. So this is negative infinity to infinity. So that's the function we're trying to graph. If there's something that I've noticed from the last 2 tests, it's that the transformation stuff is a place where we need a little bit more practice. I think it is both a bit abstract and maybe a little bit hard to remember, but it's also one of the most important things for a calculus student to be comfortable with, because being able to kind of quickly picture a graph is is so helpful for figuring out whether your answer in calculus makes sense or not. So with that in mind, and because the department changed how we do these things called GELOs, which are General Education Learning Outcomes, you may remember another thing from our syllabus day. The syllabus says that GELOs, General Education Learning Outcomes, are statistics tracked by the state that are measured on the final exam. The department has decided to stop measuring them on the final exam and start doing them as separate assignments throughout the semester. So in a second here, I'll give you a second to finish getting all the details from this graph down. But in a second here, I'm going to show you a little worksheet that you'll be filling out. It has to do with transformations. It is required, but because it's not something that I knew we were going to have to do at the start of the semester, it's something that I don't have built into the grades. So the way we're going to do this is that by doing this transformation worksheet, you'll earn a couple points back on the last midterm. So I'll hang here for about 10 more seconds, and then we're going to take a look at that. So more practice, put this in the notes here, more practice. With transformations. In homework and the Jello worksheet, which is on Canvas. It's not an ideal situation to learn, 2/3 of the way through the semester that we need to change how we measure these statistics, but it's also not that big a deal. The way this is going to work, I mentioned the state every year, in order to track how effective the community colleges are at teaching what they want us to teach, have us put a number of specific sorts of questions on final exams for a few different classes: college algebra, pre-calculus, Calc 1, Calc 2. Those classes all have GELOs. And whereas in the past, I had a few questions on the final. If you got those right, then you earned the GELO credit. If you didn't get those right, then you didn't earn the GELO credit. And none of it had any effect on your grade. It was just for the stats that we passed along to the state. Because we're not doing them on the final anymore, we have to do them with worksheets. So let me show you this GELO worksheet. Here it is. All right. So this is a worksheet I'm going to post to Canvas for you to complete. You can either print it out and do the work on the page, then scan the page, or if you have like a tablet or something like that with a stylus and you want to work on it in the PDF, that's okay too. But I'm going to post this to Canvas, and it's a very straightforward thing. It just has a couple questions. So there's a graph of a function here, not any function that we have an algebra formula for. It just, here's the curve, right? Here's the graph. You're going to be asked to do the following things. So first, you're going to tell me how to get the graphs of these new functions, f of x minus 2 and f of x minus 2, from the graph of the original, right? So shift up, down, left, right, reflect, whatever. You're going to tell me the transformations. That's problem 1. Problem 2, I've given you this graph just blown up a little bit bigger. You're going to graph both of the functions from problem 1 on these same coordinate axes. So go ahead and apply the transformations, graph the resulting function. Problem 3, you're going to tell me whether that original function f is even, odd, or neither. And you may want to look back at your notes to remind yourself what it means for a function to be even or odd. And then the last problem here is nothing to do with that graph, totally separate. We say if I've got some other function f of x and f of 4 is equal to 3, then I define some new function k to be 2 plus f of x plus 1. And I want you to tell me if f of 4 is equal to 3, what point must be on the graph of this new function k? So just these 4 problems. I think you'll sit down, and I think printing it out, completing it, scanning it, and uploading it will take you all together about 15 minutes. Not a big deal. Every question you answer correctly here will earn you 1 bonus point on the last midterm. So you can increase your score on that last midterm by up to 4% points, which is really nice. That's halfway through a letter grade, basically. You can easily bring a B to a C to a B or a B to an A. This is a required assignment, although it's not something that's baked into the syllabus in a nice way because it's a new thing that they just dropped on me. I do need you guys to do it because we're no longer allowed to do jellos on the final. So in order to get these stats to the state, I really do need everybody to do this. I'm going to give you 2 weeks to do it. I don't think for your class I've uploaded it yet. Let me see. No, it's not there yet, but I'll show you in my other 1140 class. So the transformation jello worksheet, right? I'll post this same announcement for you guys. I'll link it here and it'll also show up as an assignment. The assignment is where you're going to actually do the thing, transformation jello worksheet. And you can download it there as well. So you're going to print out the worksheet, fill it out, scan and upload the completed version. You do need to do this, right? It's a required thing for the college and for the state. And every question you get right, you get 4 bonus. Every question you get right, you get 1 bonus point. So 4 total possible bonus points for exam 2. The catch here, because this is a jello, it's a state thing. You can't work with other people, and that includes tutors. And you also can't share your answers with anybody. So please, it's a short, simple assignment. Complete it on your own. Take as much time as you want. I'm going to give you like 2 weeks. I'm going to have this open for 2 weeks for you guys to get in there and do. So please take the time to do that jello worksheet. It'll earn you some points back on the last test, and it's a necessary thing for the college. Okay. I want to look at some more domain problems for logarithms. See how that new domain red flag can interact with some of the things that we've done in the past. And then I finally want to solve that equation, 2 to the x equals 3 for you. Let's give a few examples here. How about let me see. Yeah, let's do this one. All right. So here are 3 logarithm functions, and I would like to find each of their domains. In each case, we only have the 1 red flag present, right? None of these have any variables under square roots. None of these have any variables downstairs in a fraction. All of them have variables inside of logarithms, though. So in each one of these, we need to be careful to make sure that that domain red flag, variables inside logarithms, is satisfied or taken care of. So what do I need to make sure for this guy? If I'm trying to find the domain for the function in part A, what is the inequality I need to solve? Remind you the rule up here. If we have variables inside logs, we need to make sure that inside is greater than 0. So how do I find the domain of this first guy? What's the inequality that I set up?
Two x plus 7 is greater than 0.
Hell yeah. So this function will be happy as long as its inside is positive, right? This function is a logarithm. He's happy as long as you don't try to plug any negative numbers into him. So here we need to solve 2x plus 7 is strictly greater than 0. And since this is a linear inequality, it can be solved just like an equation. Don't have to think too hard. You just subtract 7 from both sides and then divide both sides by 2. So x here has to be greater than -7/2. So my domain is -7/2 to infinity, right? Or -3.5 to infinity. The second guy requires the same sort of thing, right? Set up the same inequality. The inside is greater than 0. That would mean x squared minus 9 is greater than 0. How do you solve an inequality like this?
You would factor it.
Very good. This is a polynomial inequality. And in order to solve polynomial inequalities, you pull everything to one side. That's already been done. And then you factor and get your cut points. So x squared minus 9 factors as x minus 3 times x plus 3. And it's that which I need to be greater than 0. The cut points are the x values where x squared minus 9 can go from being positive to negative or vice versa. And those come from these factors. So that's -3 from the second factor and +3 from the first factor. And this splits my number line up into several regions. In each region, this inequality will either be satisfied or will not be satisfied. Either this thing will be positive or it won't be. To the left of -3, we could test some number like -4. Between -3 and 3, we could test some number like 0. To the right of +3, we could test some number like 4. Or we could use the end behavior for this polynomial and the multiplicity trick, or you could test one region and use the multiplicity trick. It's entirely up to you. If you test x equals 0 here, then you get 0 squared minus 9 is greater than 0, which just says minus 9 is greater than 0. So this apparatus is -9 when x is 0. In other words, it's negative in here, which is not going to be a part of my solution set. And by the multiplicity trick, that means he has to be positive in both of these regions. Or you could say that the end behavior for this polynomial is up on both sides, which means he's got to be positive in the two outer regions, and then by the multiplicity trick, negative in the inner region. So the domain here, the domain for G is the solution to the inequality x squared minus 9 is greater than 0. What is that? We've done all the work. We just have to write down the answer now. Where is x squared minus 9 positive?
Negative infinity. No. Yeah, negative infinity to -3 unioned with 3 to infinity.
Perfect. Yeah, the two outer regions, right? From negative infinity up to -3, that's this region. We're positive in here. And from 3 to infinity, we're positive here. We just want to chop out this middle piece. So that is my domain. Right? All right, this next one's kind of fun because I have two different log pieces. Here it's not a natural log, it's the base 10 logarithm, but that has no effect, right? Variables inside any sort of log. You just got to make sure the inside is positive. But there's two separate insides to consider. So on the one hand, I need x plus 2 to be positive. And on the other hand, I need 2 minus x to be positive. And those could each give us different restrictions. And if I want this whole function to be happy, I need both of these to be happy. So we need here, we need both x plus 2 to be greater than 0 and 2 minus x to be greater than 0. Now this first guy means x is greater than -2. And the second guy, you could say, handful of ways to do this. I think the easiest way is to add x to both sides. I could say 2 is greater than x, which is the same as saying x is less than 2. If you want to, you could subtract 2 from both sides, and that would give you -x is greater than -2, and then divide both sides by -1, which would give you x is less than +2, because when you divide by a negative, the inequality flips over. So I need to make sure both of these are satisfied at once. X has to be at once bigger than -2 and smaller than +2. So that first guy, x's which are bigger than -2, that's everything here. And that second guy is everything here. So what I'm looking for is the overlap of those two solution sets, which is this stuff, the stuff that is between +2 and -2. So here my domain is the interval from -2 to +2. Any questions on these examples here? Okay. So that's it for this current homework set, right? The homework set that I popped for you guys this morning, which is due again on Wednesday of this week. It is a short one, but you do need to start on it like today in order to get it done by Wednesday. There's only 14 questions. Some of them have you graphing functions by making some tables. Some of them have you identifying the graph that's given here. So this is some logarithm. What is the logarithm? Just based on the graph. Others have you transforming graphs, nothing crazy, giving domains and ranges. And then the last few are like what we just did, finding domains. Right? Very similar to the problems we've done there. I can do a quick example of something like number 4 here. I don't mind doing that. And then I want to finish up by showing you how we're going to proceed, what we're going to be doing next.
I have one question.
Sure, yes.
It's regarding like the last two exams that we have, the midterm exams, because I just realized we have like 3 weeks left, and I was wondering, like, are we gonna have one big one and then a final, or are we gonna have like 2 separate midterms?
2 separate midterms than the final. So we're almost done with the logs and exponential stuff. This week, we're going to finish logs and exponentials. And then we'll have that exam probably next week or early the week following, depending on how much time we need to review. And then we're going to talk about matrices and systems of linear equations. And that'll be the last big topic for the class. And that very last exam, that 4th midterm exam, I might end up giving you that as a take home. We'll see. It kind of depends on how exam 3 goes. But we will have 2 more midterms and then the final.
Okay, and for the when we show our documents, is this supposed to be in JPEG?
No, so uploaded scan should always be PDFs.
Ah, okay. Because I remembered one of mine is a JPEG and I can't even see anything now.
Oh, that's interesting. Yeah, the reason I request you guys use Cam Scanner or Adobe Scan or the Notes app is precisely for that reason, right? When I get in there and make comments in Canvas, Sometimes if you use a JPEG or a PNG or a HIC file, something like that, it will glitch out and cause you some trouble. I can take a look and see if there's something I can do, maybe download it and email it to you. If you want to send me a message letting me know that you're having trouble viewing the comments, just go ahead and do that. Send me a Canvas message and I'll see what I can do.
Okay, thank you.
Of course. All right. So a couple other exercises. Let's say find the function f of x equals log a sub x graphed below. And let's give the graph kind of generic looking logarithm. And we'll say that this point right here is 1/9, comma, -2. All right, so you do have a few things like this on your homework. We've only got 1 point. There's really nothing else to this, right? We know that the function is the log base a of x for some base a. And we know that the point 1/9, comma, -2 is on there. So this is very similar to those exponential problems we had in the past. Since 1/9, comma, -2 is on the graph, f of 1/9 must be equal to -2. And then since f of x has to be the log base a of x for some number a, this means that the base a log of 1/9 has to be equal to -2. So we want to ask ourselves, what base logarithm would give me the base a log, that base, of 1/9 equals -2? And it might be helpful to rewrite this as an exponential statement. This is the same as saying a to the -2 equals 1/9. All right, any ideas what we can do with this?
Would we try to like factor it?
Well, it's not so much a polynomial statement right now, so there's not a whole lot of factoring we could do, but maybe I could try rewriting it in some way that would help. A few ideas. A to the -2, that's 1 over a squared. So 1 over a squared is equal to 1/9. Is there a way I can write 1/9 so that it looks like this? Is 9 the square of anything?
Yes.
Yeah. I could write 9 as 3 squared, right? Or maybe it's a little bit cleaner if you think about it like this. If you take reciprocals on both sides, that means a squared has to be 9. So a would be plus or minus the square root of 9, which is plus or minus 3. And since a must be positive as the base of a log slash exponential, we know to use the positive guy. In other words, f of x here is the base 3 log of x. That is the function that's graphed above. And you can get it just from that one point. All right. So you have a few problems like this, and these are not the only way to think about them, but I think it's probably the most direct way. I welcome you to solve them however you like. But if you're feeling stuck, use this as a model, right? This fact that this point is on the graph always means f of that x value is that y value. And then you just say, okay, well, f is the base a log. So that means base a log of 1/9 is -2. And if you don't know what to do with this, you can always rewrite it as an exponential statement. That's what we were doing for the most part in that last homework set. And then once you have it in this exponential form, you've turned this into a problem of the sort that we had on the last homework set. You just have to solve this for a. Okay. I promised to tell you how we solve 2 to the x equals 3. And we've now spent 2 classes talking about logarithms, but I haven't shown you exactly where that comes from yet. So we started talking about logs with the equation two to the x equals 3. And I said logarithms were necessary to solve this. Two to the x equals 3 can be solved by doing a special new operation. And that special new operation is taking logarithms. So just like you can square both sides of an equation, or you can take the square root on both sides of an equation, you can take logs on both sides of an equation. And since this is a base 2 exponential, I can solve this equation by taking the base 2 logarithm of both sides. I'm not multiplying by log. This is not multiplication. I'm taking both sides and plugging it into the base 2 logarithm. On the right-hand side, this is just a number. It's the base 2 logarithm of 3. On the left-hand side, I can use that property of logs that we wrote down both last time and at the start of class this time, that the base a log of a to the x is always just x. So x is the base 2 logarithm of 3. And that is that 1 point, whatever it was. There is no really nice way to grab this. I will eventually show you a way to get there with a calculator, but 1.58496. This is the exact answer. You just call it the base 2 log of 3, and this is an approximation. Which is why when we plugged this number back into that equation, we didn't get exactly 3. We got like 2.9999999. Moving forwards, we will be doing lots and lots of this, solving equations like this. Many considerably more sophisticated equations that reduce to things like this. But before we get there, solving exponential equations, log equations, we need to talk about some more properties of logs. Algebra properties of logs. There are a few basic rules here, and I will share them with you quickly. Well, maybe not. I'll just say this for now, since we're about out of time. Each log rule comes from an exponent rule. Again, because we don't have like a clean algebra formula for the logarithm, there's no hope of developing properties of logarithms straight from a formula. But remember those basic rules we had, like a to the x times a to the y is equal to a to the x plus y. We had one that said a to the x divided by a to the y is equal to a to the x minus y. And one that said something like a to the x all raised to the y is a to the x times y. Each one of these has a buddy in log land. I'll go ahead and show them to you right now, but we'll reiterate this next time. And then we will practice with them. And then we will use them to solve equations. This first one is equivalent to saying that the base a log of a product of two numbers, x times y, is the base a log of x plus the base a log of y. So logarithms take multiplication inside and turn them into addition outside. If you want to, you can think of this rule as saying exponentials take multiplication outside and turn them into addition inside. Logs do the opposite. This rule says exponentials take division outside and turn it into subtraction inside. So the corresponding rule for logarithms says division inside becomes subtraction outside. And this last one is maybe the most important. This guy says that powers outside become multiples inside. And the corresponding rule for logarithms is that powers inside become multiples outside. Oops, sorry, log a of x. All right, so these are the three basic log properties, or log laws, your textbook calls them. And our next lecture is going to be all about these log laws and how we can use them to expand and simplify logarithm expressions. Those will be useful because when you go to solve more complicated exponential equations, your first step is going to be to take logs. And if that equation is somewhat complicated, you may end up with stuff like this: multiplication inside a log, or division inside a log, or very often a power inside a log. And you'll use these properties to simplify them and break them down to things that look like this. The other thing I'm going to show you next time is how to take this and punch it into your calculator in order to get this. Obviously, you can do what I did here and go over to Desmos and just type it in. But there is a formula that allows you to compute the base a log of b, where a and b are any numbers. As long as that base is positive and the inside is positive. So that's where we are and that's where we're going. Please work hard on this homework set that I just popped for you. Next time, log laws. Time after that, exponential and log equations, and then we're done with exponentials and logs and we'll be ready for exam 3. The remainder of the course is going to be focused on systems of equations and matrices. There will be a small discussion of sequences and series at the end. There is also a section on conics, which I think we may not have time to get through in detail, but I'll probably provide you some sort of worksheet or something like that. The other thing I'm going to ask you to be mindful of is this transformation Jello worksheet, which I'll be posting to Canvas for you today. Remember, this has the ability to earn you some points back on that last test. Everybody loves that. And it is required. It's not an optional thing. It is a necessary thing. You're going to have 2 weeks to get it in. So that's it for me. I'll see you guys next time.